All right, I'm a little early, but let's go ahead and get started. So yeah, I'm sorry I was not here on Wednesday. I ended up getting suddenly very sick, but luckily, yeah, I was able to find somebody on short notice to fill in. It sounds like he got pretty deep into section 9.3, so the polar coordinates. Um, so the things that you've hopefully have talked about at least to some degree is what are polar coordinates? Like, why would we use these instead of rectangular Cartesian coordinates? How do they work? How do I talk like translate between the two? What do some graphs look like? Things like that. If there's any questions you have from last time that you want to revisit right now, we absolutely can. Or if you feel good about everything, we can just kind of pick up from. It sounds like you might have finished this one, started it. Okay. All right. So we'll pick up right here. Just a couple of announcements. I have tests for you. So if you want to come pick yours up at the end of class, please do. Everything in Canvas should be very close to up to date. So I've reconfigured the gradebook so it drops some homework assignments. The final exam will still replace a midterm grade if it helps you. What else? So they said the only grades that are going to go in there now are the written homework that was due last night. The written homework that's due like in a week. I think it's the 1st of December, something like that. And then there's one like when's the web work due for this for 9.3? Thursday. So 2 more web works, 1 more written homework assignment, and the final. So I mean, you should hopefully have a clear picture of kind of where you are. But if you have any questions, please let me know. I do not have any final exams myself this semester, so I'm pretty available. So let me know if you need to talk. What else? If you haven't already filled out the course evaluation, please do so. Colin?
Is our final in here?
Is not. That reminds me of one more thing I wanted to talk to you about. There is a quiz. Quiz is a very, very liberal term for what that thing actually is. It's just basically it's me offering you free points to figure out when your final is and where it is and all that stuff. Have you seen that? I think I posted and published it. Okay. But basically, it's 5 questions, multiple choice, infinite attempts. Basically, ask you where the final is, when it is, all the pertinent stuff. Short answer, no. The final exam is not in here, unfortunately. It's close, but it's not here. That's a good question. What day is the final? The 5th, week from tomorrow. That's one of the questions. That's 2 points for you. But yeah, that's I intend for that to be free points for you. Unlimited attempts. And I think all the answers I have either said in here or put in the syllabus, so should be good to go there. What else, Haley?
Like what category of our grade like deals with homeschooling?
Online homework.
Okay.
So basically, it's essentially a dropped. I mean, it's 10 points, just like all your other online homework. So it's basically a free one.
Okay.
What else? Okay. Thank you to those of you who have filled out the course evaluation. I think it's up for another couple of days. I think it closes on the 30th. All right. So it sounds like you started talking about, how to find slopes of tangent lines when you're dealing with functions written in polar. So why don't you tell me what do you remember about that? How do you find those slopes? Or just in general, how do we find the slope of a tangent line? That used to be the kind of question you could answer with a single word. Now you got to be a little more specific. But if I want to find the slope of a function or the instantaneous rate of change of a function, what do I need to do? What kind of operation do I need to do? I need a derivative, right? So I need a derivative, but I have to be specific about what derivative I want. So just kind of like we were talking about parametric equations, the derivative is not good enough anymore because there's lots of variables talking about.
You want dy dx.
We want dy dx, right? So we want dy dx, but I am not giving you a function that is expressed in y and x. I'm giving you this function where r is a function of theta. So did he talk to you about how you get dy dx from the things you have? How do we do that?
The derivative of dy d theta over, yeah.
Okay, so very much like the way we set up a parametric derivative. So dy d theta over dx d theta. How do we find dy d theta and dx d theta? So he talked about how to convert between polar and Cartesian, right? Can I represent y in terms of polar coordinate language? I think I saw this diagram earlier. Not sure how much you talked about it, but polar coordinates basically tell you these two things. If you're on some heading theta, that's what theta represents, is like a direction you're going from the origin, and r tells you how far along that heading you're going, right? Where Cartesian gives you a pair of distances. How far away are you from the origin horizontally, and how far away are you from the origin vertically? So if I relate them to this right triangle here, how can I relate y to r and theta? Yeah, y should be equal to r sine theta, and x should be equal to r cosine theta. So basically, for both of these, I'm taking the derivative of r sine theta with respect to theta, and I'm taking the derivative of r cosine theta with respect to theta. Is this set up something that you've all done, or? Okay. Let's speed up a little bit then. How do I find the derivative of r sine theta with respect to theta? Should need product rule, right? So I'll take the derivative of r with respect to theta times sine theta plus r times the derivative of sine with respect to the derivative of sine theta with respect to theta, which should be negative cosine theta all over dr d theta cosine theta plus r sine theta. So this complicated expression, that's dy dx, right? Go ahead. Oh yeah, I did the negative in the wrong place. Yep. Okay, so what is dr d theta in our case? Should be cosine theta, so I should get sine theta cosine theta plus what's r? 1 plus sine theta cosine theta all over cosine squared theta minus 1 plus sine theta sine theta. So questions how we got there? Did you already do the top bullet where theta equals r, so where theta equals pi over 3? Okay. So let's go ahead and skip forward then. How do we find where the tangent is horizontal? What does that mean for the tangent to be horizontal?
The numerator 0.
So the numerator should be 0. What about the denominator?
Be not 0.
Right, so that's what we want. I would like for dy d theta to be 0 and dx d theta to be non-zero. So what's our denominator here? Or sorry, numerator. Sine theta, cosine theta. Is it worth it to expand this? Maybe not. So 1 plus sine theta, cosine theta equals 0. Actually, I think we should. So sine theta, cosine theta plus cosine theta plus sine theta, cosine theta equals 0. Two sine theta, cosine theta plus cosine theta equals 0. Okay. Where can I go from here? Go ahead.
Two sine theta cosine theta is the double, right?
It is. You're right. I'm gonna push back on that. I don't know if that out.
Okay.
I can see where that's going. And I just think it's gonna make it more complicated.
You factor cosine theta.
I think we can factor in cosine theta. So that becomes 2 sine theta plus 1 equals 0. Does this give us any clue about what angles I'm actually looking at? Where does cosine theta equal 0? Pi over 2. 3 pi over 2. And what else are we looking at? I want to know where sine of theta is equal to -1/2. So that should be 7 pi over 6. 11 pi over 6. So I believe those are all the angle measures. They're going to give you a horizontal tangent. Questions? Go ahead.
Do we need to check the denominator now?
Yeah, we should. So yeah, we should check the denominator just to make sure, like, I mean, that'll kind of give us both the things we want. I would like to know if any of these angles need to be eliminated, or I also wanted to find out where this is vertical. So if I want to find out where tangents are vertical, does the denominator do anything good for me? It kind of does. So I get cosine squared theta plus sine squared theta. No, I don't. No, that's gonna be too easy. Cosine squared minus sine theta minus sine squared theta equals 0. I don't see anything factoring. Is there anything I can do here? There's a trig identity I can use. Which one would you like to use?
Substitute cosine squared theta for 1 minus sine squared theta.
I can do that. So if I do that, I get 1 minus sine squared theta minus sine squared theta minus sine theta equals 0. I'm running out of room. How does this factor? Still don't think it does. Yeah, in fact, like a quadratic. So 2 sine squared plus sine minus 1 equals 0. Did someone say that factors down? Okay. I'm gonna get real clumsy with where I'm gonna go next, but how does that factor?
1 plus 2 sine theta.
1 minus 2 sine theta. All right. So what angles is this going to give me? sine of theta equals -1 at 3 pi over 2. And sine of theta equals 1/2 at 5 pi over 6. And pi over 6. All right, so what have we learned? Where is the tangent actually horizontal? We found 4 candidates. I don't think it's actually horizontal in all 4. Or do we think it is?
It's not horizontal at 3 pi over 2.
3 pi over 2, nor is it vertical there. Basically, that's undefined there. But I do believe it is horizontal at these 3 angles and vertical at these 2. Questions? There was a lot of algebra that went into that, so if we need to recap anything, let me know. Okay. Let's go ahead and move on. So now I want to find the equation of the tangent line. So yes, the slope, but I want to go a little further than that. So I'm giving you a polar function here. I want to find the equation of the tangent line. How do we start about that?
Dy dx.
Okay. You're going to find dy dx. So that is going to be, the process is going to be identical to kind of what we did. So I'll go ahead and shortcut this a little bit. So it'll be dr d theta. I don't remember the rest of it, so let's go steal it. All right. So let's start filling in these pieces for our specific equation. What is dr d theta for us?
What's right there?
8 cosine theta, thank you, times sine theta plus 3 plus 8 sine theta cosine theta. Okay, so here's my derivative. What should we do with that? So this big expression we just built, what did we do this for?
Plugging theta to find the slope of that theta.
Right, so now that we now plug in this theta value, this will give us the slope of the tangent line. All right, what is the cosine of pi over 6? Radical 3 over 2. This is a mistake. there any chance this simplifies to something friendly? Don't approximate that for me. Or do we want to keep it exact? Okay, so a long way to go, but we got something. We got the slope of that tangent line. So how do we get the full equation of that line? Go ahead.
I feel like you switch the sign of the meaning right there.
In the numerator,
You plug it in.
cosine of pi over 6 is
Yeah, that part looks right, on the right.
yeah, you're right. Okay, what did that do? So 2 radical 3 plus 3 radical 3 over 2. All right, good catch. I think that's better now, right? Okay, I think that's as simplified as I'm going to make it. Unless there are more errors, which there could be.
So -3 out.
Minus 3 halves. So 8 times 3 over 4 is 6, right? Did I go too fast with the 3 halves? Let's see. 3 plus this. This is essentially 3 plus 4 right here, right? So 7 times a half. Oh. Yep. So 6 minus 7 halves is what?
Five.
All right. Are we happy now? Should have just slowed down with it. Okay. If we're happy with that slope, now what do we do with it? Because we want to find the full equation of this tangent line. So what else do we have? What else has to happen? Go ahead.
Y theta, and then.
Okay, so yeah, let's find those values. If theta is equal to pi over 6, how do I find a y value? If I want to find y in terms of polar coordinates, what do I really need to do? So think about how you convert between polar and Cartesian. I think this is actually something we've done in the last slide or two.
Y is equal to R sine theta.
Y is equal to r sine theta, and x equal to r cosine theta. So y is going to be equal to 3 plus 8 times the sine of pi over 6, all times the sine of pi over 6. So that should be 7/2. No?
No,
Oh, okay, sorry. And 3 plus 8 sine pi over 6, or cosine pi over 6. No, I was right the first time. This whole thing is r. This is the cosine. So the bracket is still 7. So this will be 7 radical 3/2. So I have a y value, I have an x value, I have a slope. So I have everything I need to write out an equation of a tangent line. Point slope form is going to be way more direct than trying to find a y-intercept. So y minus 7/2 is going to be equal to the slope times x minus 7 radical 3/2. So again, long way to go to deal with finding tangents when you start from polar. So whatever questions you have, let's ask them now. Go ahead.
We don't need to.
I'm happy with that. I think the word simple has long been abandoned. Anything else? All right, so that is what I have for you for this section. I'm not sure if I've said this, but basically there's, after the third test, there's only 2 more sections. So now we're down to 1. And really with whatever time we have remaining, is kind of review. So yeah, one thing I meant to say that I did not, on the module for this week of class, I did put like some questions. Basically, I just pasted that whole thing from the back of the syllabus about questions from the book. I put another, there was no practice quiz that I could pull from, but there is like a PDF full of questions broken down by section that I think is worth looking at. But basically with whatever time we have, we might be done on Wednesday. But certainly there will be time to review. So look over those things that come with questions. Question?
This is the last one or the other one?
This one we're about to start is the last one. What else? Okay, so we did some, basically section 3 is about like getting you acquainted with polar coordinates and doing some of the differential calculus with them. Now we're going to get into the integral side of things. So what's kind of the big, or maybe the first way you were probably introduced to the integral, probably at the very tail end of Calc 1. What do we do with integrals? Or what was the first thing you probably did, if you can remember back to the end of last semester? What's that? Riemann sums. What do Riemann sums do? Yeah, so if I have a curve like this, yes, you use Riemann sums, but those Riemann sums are, I mean, one way to look at them is if I do like left Riemann sums here, I'm going to find a bunch of areas. And I don't have a easy formula for the area under whatever this shape is. But if I'm able to draw a bunch of vertical lines, what am I actually finding the area of? Those are rectangles, right? How do you find the area of rectangles? Length, so length times height, right? Or in terms of, we're looking at this in terms of functions. X times y, or x times f of x. And really, I am adding up a bunch of those things, right? In a Riemann sum, I have a certain number of rectangles. And really, for each one of those I'm doing is I am multiplying a y value times however wide my rectangles are, right? So in a Riemann sum, and by the way, when Riemann developed these, I think he first developed them for rectangles. But this idea can basically be translated to all kinds of coordinate systems. You'll learn more about that in Calc 3, but we're going to do one of those right now. So yeah, in a Riemann sum, you are finding the area under a curve by breaking up that area into a whole bunch of smaller, really simple geometric shapes. So rectangles are very easy to deal with. In polar coordinates, we don't have the same kind of luxury. It's not as simple, but we're going to use the same kind of Riemann sum approach. So maybe I want to find the area associated with this curve. So typically when you find the area in Cartesian coordinates, you find the area underneath the curve, right? Between the curve and what? It's not all of it underneath the x-axis, right? With polar coordinates, same kind of idea. We're going to find all the area underneath this curve, but bounded by not the x-axis, but the pole, the origin. So I'm going to look at this area here. But the way I'm going to look at this area is I'm going to split it up into a bunch of smaller things. What do those smaller things look like? Well, they're not really rectangles, but they're going to be like these shapes here where anyone know the name, the geometric name for these things I'm making here? Little pizza slices.
Segment.
Not segments. You're close. Sectors. So basically the Riemann sum in the polar variety here is I'm going to look at the area of these sectors. How do you find the area of a circular sector?
C to R.
What's that?
C to R.
C to R?
Yeah.
What is C?
Theta. Like,
Oh, theta R. Okay. I know what you're getting at. That is not going to give you an area. That gives you like an arc length. Basically, that gives you this little length right here. What I'm actually looking for is the area. So the whole two-dimensional area there. So let's relate it to the whole circle. How do I find the area of an entire circle? Pi r squared, right? So I don't want to find the area of an entire circle. I want to find the area of a fraction of a circle. So I'm going to use my angle to kind of set up that ratio. How many radians are in a full circle? 2 pi. So theta as a fraction of 2 pi is going to set up that area for me. Do a little simplifying and I get 1/2 r squared theta. So that's basically going to be how I'm going to set up my area in polar coordinates. I'm going to add up a lot of these little tiny sectors. So in polar coordinates, my equation is going to look like this. We're going to bound my integral from a to b. So these are going to be theta values, whatever my least theta value and my greatest theta value of 1/2 r squared, not 1r, 1/2 r squared d theta. And so this is the one we care about. I'm going to write the integral in Cartesian coordinates just to kind of give you a sense of them both side by side. But that y dx, the y really gives you a height and the dx gives you a length. So that's how you get an area of a rectangle. And in polar form, we're dealing with sectors. So 1/2 r squared times a change in angle gives you the area of a bunch of really small sectors. Once I add those all up, I'll have to find the full area. So questions on the motivation on the setup here? But the bottom line is just like a Riemann sum. I mean, there are 2 other coordinate systems you'll learn about in Calc 3. Those of you who are moving on to Calc 3. You'll probably also see built up as Riemann sums. But basically the whole motivation for Riemann sums is to bring it back to some very basic geometric shape and add those things together. So let's do one to find an area now. I want to find the area enclosed by one loop of this cosine 2 theta. So if you feel like Googling this, you can, but I think this shape looks something like, I think it actually traces out like this. I can do a better job than that. I think it's like a flower with 4 petals, something like that. So I want to find the area just of a single loop of this thing. Any ideas on how to get started doing that? So we know we're going to set up an integral, so I'll kind of set that as the baseline. I need a bounds for theta. And I'm integrating 1/2 r squared d theta. Is there any of that stuff I can fill in quite yet? Yeah. No one's asked for it, but I'm going to pull out the 1/2. This becomes cosine squared 2 theta. Do I know the bounds, or can I figure out the bounds?
That's 0 to 2 pi.
Well, I graphed what I believe is 0 to 2 pi, but that's more area than what I want. So one loop, so like this. So basically, this curve is going to intersect itself more than once. So basically, I just want to find out where this thing intersects itself and call that like a closed loop. And to make this even more clear, I didn't put this or make clear enough. They're going to intersect each other at the origin. How'd you get that? Yeah. So maybe that'll work. Let's find out. But I think the better way to go about this is to set this thing equal to 0. So if I can find like theta values, adjacent theta values where this thing intersects the pole, will be good. I just don't believe that. I don't believe theta equals 0 will satisfy this, right? All right, so how do I solve this thing?
You have to use something like that.
I don't think I do. I could. But I think I can start here. 2 theta is equal to the inverse cosine of 0.
Yeah.
What is the inverse cosine of 0? Cosine of 0 is not 0. Should get pi over 2, right? So let's do that. I think it's good to have 2 values because I know I want back-to-back values, right? So I know that cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. For this case, I don't really care about theta. I don't really care about 2 theta. I care about theta itself. So what are the angles I really care about? Pi over 4, 3 pi over 4. So I think that is a good set of bounds. So we got our bounds, we got our integrand.
Why would we equate it to 0? Because that's where you need like that origin.
Yeah,
So we're finding what's.
I think a better graph would have made that more clear, but that's what they're all going to come back to. But I don't. Yeah, I think that's the most direct way to set this up. All right, this cosine squared of 2 theta is that an antiderivative that we have? I think there's a trig identity we got to take advantage of. So let's do this one. Cosine 2 theta equals 2 cosine squared theta minus 1. So I can't integrate a cosine squared very easily, but I can integrate everything else in this. So let's solve for cosine squared theta. That should come out to be 1/2 times 1 plus cosine 2 theta. So how can I use that to finish up this integral?
Substituted with that change of the two data, so it would be like 1/2 times 1 plus cosine 4 theta.
So 1/2 times 1 plus cosine 4 theta. Are we okay with that? How about if I do this? But I think this integral is good, but I think the setup here is, as usual, the most challenging part. Any questions about how we got here? If not, then let's go ahead and do it. What is this antiderivative?
4 times theta minus sine 4 theta divided by 4.
How do we feel about that? Think there should be a positive sign between them?
Why is it possible?
What's the derivative of cosine?
Oh, wait. Yeah. Oh, wait, never mind.
Unfortunately, I don't think we ever get comfortable with that derivative or antiderivative ever. I always get worried about it.
And then I actually need to figure it out, so.
All right, so 1/4 times 3 pi over 4 plus 1/4 times the sine of 3 pi, which is 0, minus pi over 4 plus 1/4 the sine of pi. So what do I get? I get 1/4 times pi over 2. So pi over 8. Questions? All right. So just like we did, I think the very first thing we did, or one of the very first things we did was find the area between two curves. That's the kind of thing we want to set up now. So how would you like to start that? I don't think we're going to finish this here, but we'll at least start the setup of it. Or remind you of the,
Oh, so it's like it's like a segment, like it's like a part of the circle.
is there even a circle?
I mean, like, no, it's like like that. I don't know.
It's going to be like, it's probably going to be a loop again, because we're graphing like both of these things depend on the sine of theta, and we know the sine of theta repeats. So I think it's safe to assume we're going to have a closed, at least one closed loop here. So basically, as we let theta increase, it's just going to kind of keep drawing over itself, basically. So knowing that, yeah, what's a good place to start here? Huh?
Which function is above the other? Or like,
I'm gonna push back on the word above because, and the reason I'm gonna push back on the word above is this. Which one of those curves is greater if I'm looking in polar? The bottom one, right? So greater in polar means further from the pole. So yeah, I'll amend above to mean greater, but yes. So how do I find which one of these things is greater?
Like inside and outside, so can you like find out the candidate? I feel like all three sine theta is great.
That's probably safe to assume, but does that mean does that mean that one's always greater? For any value of theta I can ever pick? No. So is that a good enough hint for you? I think we know which one's greater and which one's lesser, like in the span that I care about, but I don't think I know what that span is. So how do I find those theta bounds?
You have to equate them, like where they move.
I think equating them is good. Because that's when that's how I'm gonna find the region, is when these curves are actually related in the way that I'm asking about. So it's 3 sine theta equals 1 plus sine theta. Two sine theta equals 1. Sine theta equals a half. Which gives me what theta values? So I believe we have a good set of bounds, hopefully. Should we actually check that the relationship we have is good there? Can we actually make it? So which one's supposed to be greater? 3 sine theta? Can we make sure that 3 sine theta is actually greater?
Like, put the value between those bounds.
That's a good idea. So what's a good value between those two? Pi over 2 sounds good. What's 3 sine pi over 2? 3. What's 1 plus sine pi over 2? 2. Sounds good. So I think we have a good set of bounds. The area is equal to 1/2 times the integral from pi over 6 to 5 pi over 6 of what?
So now we have to subtract the gradient, right? Like 3 sine theta minus 1 plus sine theta.
So that's a good question. Do we just do radius 1 minus radius 2 and then square that whole thing? Let's think about this. Let's go back to the geometry of it all. We talked about how to find the area of a sector. What we didn't talk about is how to find the area of a thing like this. So let's say I have a sector, but I don't want to find the area of that sector. I want to find the area of this piece of it. How would you find the area of that? Just the outer piece of it.
It's like if we did it in like Cartesian, I think it's the same. I think we need to separate them until F and G, like F squared minus B squared.
So you're saying we need to square each function separately?
Yeah.
So, and that is true. And geometrically, I'll kind of try to point out why that is here. Let's say the outer radius is 6 here and the inner radius is 3. The way to find that area, I really do have to find the area of both sectors. So 1/2 times 6 squared theta minus 1/2 times 3 squared theta. So for that same reason, I have to treat these separately. So what is my outer function? Minus my inner function, which is 1 plus sine theta squared d theta. And I'm at 9:55, so let's go ahead and stop there. We'll finish that up next time. But just if you have questions now, go ahead and ask me. Otherwise, we can hold until next time. But yeah, again, I think the setup for these things is the more complicated part. So whatever you want to talk about. Otherwise, I'll see you next time. I have tests for you if you want them.